So, in the last video we have seen how to solve the Bessel equation when 2 alpha is non-zero integer. Non-zero integer I have seen, that is the corresponds to the case 2. In case 2 itself we have a special case, you do not have to calculate the second linearly independent solution by the method of Frobenius. You can see that the first solution itself will give me the way we just replace alpha by minus alpha will give you. So, alpha, so 2 alpha, so n is alpha equal to n is, so when you have alpha is 2 alpha, so difference between the 2 alpha is non-zero integer. So, you have seen when they are odd integers, when they are odd integers you have seen that you can get linearly independent solutions as j alpha and j minus alpha, okay. And when 2 alpha, the difference between the roots of the initial equation is even integer, that is same as alpha is equal to integers, alpha equal to n is from 1, 2, 3 and so on. You have seen how to calculate the second linearly independent solution other than j alpha of x, okay. So what is left is only for the case when alpha is repeated. Alpha is repeated, the difference is 2 alpha, that is alpha and minus alpha, they are repeated only when alpha equal to 0. So that is the case we see. So that we solve this case 3 now. Case 3, you consider this case when what we have seen is, we have already seen that in this case when alpha equal to 0. So we have alpha equal to 0. So the equation is simply x square y double dash plus x y dash plus x square minus alpha square, alpha is 0, y equal to 0. So this is the equation x positive. So you have already seen that this solution is y1 of x is this solution. One solution is this, okay. This is one solution. So to get the other solution, you know when the repeated roots, when the roots are repeated, okay. So we have seen that when you look at k square minus alpha square equal to 0. So k equal to plus or minus alpha. So when they are repeated roots if alpha equal to 0, okay. So in this case second linearly independent solution is, there is no arbitrary constant here. So you simply j naught, that is y1 of x into log x plus, so x power 0, x power other root minus alpha, x power minus alpha, alpha is 0, so that is simply 1. You have n is only from 1 to infinity, some dn x power n. So this is how you should look for your second solution as in the Frobenius method. So you simply solve, try to substitute this equation into the Bessel equation. So substitute this form of solution, okay. Look for y2 in this form and substitute there. So to get that, so you need the derivatives to substitute into the equation. So you have j naught of x by x plus log x j naught dash of x plus here if you repeat, if you differentiate, n is from 1 to infinity, dn n dn x power n minus 1. So this is what is the derivative. Now if you do this y2 double dash of x, again minus j naught of x by x square plus j naught dash of x by x, okay, plus if you differentiate this you get j naught dash of x. So you have repeated, so twice. So you have j naught dash of x, j naught double dash of x into log x. This is as you see, these are the 3 terms you get if you differentiate these 2 terms, and then you have n into n minus 1 dn x power n minus 2. Now this is running from x power 0, so constant. If you differentiate, it will go. So it is starting from 2 to infinity. Okay, so these 3 you substitute into the equation. So x square y double dash, that will give you minus j naught of x plus 2x j naught dash of x plus x square j naught double dash of x into log x plus n is from 2 to infinity, n into n minus 1 dn x power n. So it starts from n is 2 onwards, okay. this is the x square y dash, this is x square y double dash plus x into y dash, x into y 2 dash, that is j naught of x, x log x, j naught dash of x plus, you simply have again one is from 1 n dn x power n. Now the remaining is x square y. So that is x square into y is, so x square j naught of x log x plus x square. So this you have, and you multiply this x square dn x power n plus 2. So you see that this is what you substituted and equal to 0. So this is what is the equation. So this goes, and you see that all the powers of the series are x power n. So you here if you make it n equal to n minus 2, if you make n equal to n minus 2, so then it becomes n dn minus 2. So if you replace n equal to n minus 2, this starts from 3 to infinity. So you can see that. Now look at these three terms. So this one, this one, and this one, all the coefficients of log x. If you see this together, j naught is, since j naught is satisfying the equation, so you can see that log x times, so x square j naught double dash plus x j naught dash plus x square j naught of x is equal to 0. So because this is equal to 0, because j naught satisfies the equation, Bessel equation, this has gone. So plus, now you have 2x j naught dash of x, and then plus, now you can put it together. So it starts from n is from 1 to infinity, here n 3 to infinity, this is 2 to infinity. So common thing is from 3 to infinity. So n is starting from 3 to infinity. So you have n into n minus 1 dn, okay, plus n dn, okay, plus dn minus 2 into x power n, and whatever the remaining terms which you missed, here n equal to 2. So that will give me 2d2 x square, here n equal to 1 and 2. So here n equal to 1 and 2 will give me n equal to 1, you have d1 x plus 2 d2 x square equal to 0. So this is what you have. So if you rewrite, so you can see that d2 d2 x square, so that is going to be 4 d2 x square d1 x plus 2x j naught dash of x plus, this is running from 3 to infinity. So you see that here n into n square minus n plus n. So that is going to be simply n square dn plus dn minus 2. Okay, so into x power n equal to 0. So what is your j naught? J naught of x is actually equal to, so you can rewrite. So that is you have already seen what is j naught. J naught is 1 plus sigma m is from 1 to infinity minus 1 power m x power 2m plus alpha is 0. So divide by 2 power, so you have x by 2 power 2m plus alpha. So you have 2m m factorial comma of m plus 1, that is m1 one more m factorial, that is square. So this is what is your j naught of x. So you need j naught dash of x, so that will give you, that is 0. Here this will give me simply m is from 1 to infinity minus 1 power m x power 2m minus 1, okay, divide by 2 power 2m into m dash square. This is what is your j naught dash. So you go and substitute into the equations wherever in here j naught dash. So you get, so it starts from x onwards. So x and so if you see this, this series is starting from x cube onwards. This is x square. This is starting from x. Okay. So, x, x cube, x 5 and so on. So, j naught dash is actually x powers of odd. So, finally, you get this d1x plus 4d2 x square plus 2x. 2x you multiply, so 2 times. So, if you do this, if you replace, m is from 1 to infinity minus 1 power m x power 2m divided by 2 power 2m minus 1 m factorial square. This is what is 2x j naught dash plus n is from 3 to infinity n square dn plus dn minus 2 into x power n equal to 0. So, now you can equate, these are odd, these are now only even terms. So, x square, x 4 and so on. So, this is running from x 3 onwards. So, you equate the coefficients of lowest, so coefficients of starting with x equal to 0 will give me, so d1 equal to 0. Okay. d1 is the coefficient of x. So, coefficient of x square equal to 0 will give me, what is the coefficient of x square? 4d2 and here m equal to 1. So, that corresponds to minus 1 by m equal to 1. So, you have 2 and you have m equal to 1 fact. So, it is simply half, okay, plus, and this is 0. So, that is going to be 0. So, this will give me d2 equal to 1 by 8. Okay. And similarly, coefficient of x cube equal to 0. So, this will give me x cube. What is the x cube here? So, you have, there is no, these are all even. So, you have only here. So, that will give me n square d3 plus d1 equal to 0. Because d1 is 0, d3 has to be 0. So, implies d2n plus 1 equal to 0 for every n 1, 2, 3 and so on, because of this. These are all odd. These are all the odd coefficients, okay, x power of odd number. So, that coefficient has to be 0. So, from this, because d1 is 0, d3 is 0, d3 is 0, next time d5 will be 0 and so on. So, you will get all the odd coefficients will be 0. Only now we have to consider coefficient of x power let us say 2m equal to 0 will give me. So, start with, if you want you can say simply see x power 4. X power 4 will give me, you get m equal to 2. So, you have 1 by 2 power 4 minus 1. So, 3 2 factorial square, okay, plus n equal to 4 is 4 d4 plus d2. Okay, so, 4 square d4 plus this is equal to 0. So, this will give me a d4 equal to minus d2 minus 1 by 2 cube 2 factorial square divided by 1 by 4 square. So, what is d2? d2 I know already is 1 by 8. So, we have 1 by 4 square minus comes out. So, 1 by 8 1 by 2 cube into 1 plus 1 by 2 factorial square. So, this is what is your d4. So, like this you can get coefficient of x5 0. If you make it equal to 0, you see that d5 will be 0. So, that we have already seen here. So, you make it equal to 6 equal to 0. So, you see that d6 will be. So, for this you have to use m equal to 3. M equal to 3. So, you have minus 1 by 2 power m equal to 3 5 3 factorial square plus 3 square. This is n equal to 6, right, x power 6 you need. So, n equal to 6 here in this series. So, n equal to 6. So, 6 square d6 plus d4 equal to 0. So, this will determine d6 in terms of, again you know what is d0. So, substitute and get your d6. This is going to be 1 by 6 square minus d4 minus 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 plus now. So, 1 by 2 power 5 3 factorial square. So, d4, so now d4 you could substitute, so you can see that some number, okay. Minus d4 is 1 by 4 square into 1 by 2 cube 1 plus 1 by 2 factorial square, okay. That is what is my d4 plus 1 by 2 power 5 3 factorial square, something like this. So, you get this d6 and so on and so on, okay, and so on, you get all other coefficients. So, go back and substitute here all coefficients into your second solution, which is in this form. So, what are the unknowns? Only to get dn's, so which you have found, okay. So, that is your second solution. Again here you can define whatever you get here. So, after getting these coefficients, that is actually whatever you get. So, y2 of x is actually Bessel function of second kind of 0th order, because alpha is 0, Bessel function we can write y0 if you want, y of 0. You have seen earlier yn of x and alpha equal to n. Now, you see that yn of x, by definition this is your form y2 which is given here, okay, with all the dn's which you calculated here. So, that is how you define second Bessel function of second kind of with the order alpha equal to 0, okay. Bessel function of 0th order of second kind Bessel equation of order 0. So, this is how you get this y1 and y2, which you simply applied the Frobenius method to find the general solution. So, general solution of Bessel equation in this case is y of x. This is the case corresponds to alpha equal to 0. y1 is simply c1 y1x. y1 we know already, this is j0 of x plus c2 some arbitrary constant, that y0 of x, that is your y2, okay, which is just calculated. So, this is your general solution of the Bessel equation in the case when alpha equal to 0. So, we have seen the special case when 2 alpha is odd integer, odd non-zero integer. That means 2 alpha is 1, 3, 5 and so on. In this case, general solution you have seen that c1 times j alpha of x plus c2 j minus alpha of x is what you have already seen, okay. This is a special case. Only when the alpha 2 alpha is 2, 4, 5 and so on, 2, 4, 6 and so on, when it is even, that is same as saying this is alpha is 1, 2, 3 and so on. You have seen the general solution is c1 times j alpha of x plus c2 times y alpha of x. This is unbounded. You can see that the second solution, because of log x term, yx is unbounded. Here j alpha of x is also unbounded because of x more minus alpha. And what else you have seen? So, this is what when 2 alpha is integer. So, when alpha equal to 0, so we have already seen this one. So, this is the case, this we have seen. So, when alpha is non-zero, so when 2 alpha does not belongs to z, any integer, in this case again it is the same style. So, that is like this type, c1 j alpha of x plus c2 j alpha of x, okay. So, this is how you get whatever may be alpha value, depending on the difference between the roots of the initial equation, you have the general solution of the Bessel equation. But in this special case you have this one, but these are this you can calculate in a different way, that will using the properties of these Bessel functions, okay. So, we will have certain properties of Bessel functions. We'll start with, so you know what is j alpha of x. So, let us write what is j alpha of x, and then you can just write the properties, okay. So, having known what is j alpha of x, 1 plus sigma m is from 1 to infinity minus 1 power m x by 2 power 2m plus alpha divided by m factorial gamma of m plus alpha plus 1 This is what you have, right. So, property 1 is you differentiate this. If you differentiate actually, so you have x power alpha corresponds to m equals to x, you have x power alpha here. So, x power alpha, so this we can combine it and say that m is from 0. So, if you put m equal to 0 also, you see that 1 power m 0, so x power 2 m plus alpha. When you have m equal to 0, what you have is simply x power 2 alpha. So, this is what you have, divide by m factorial gamma of m plus alpha plus 1. First property is, if you differentiate, I will differentiate this, multiply x power alpha and you take this j alpha of x. What you get is x power alpha j minus alpha of x. Second one is, if you replace alpha by minus alpha, you take the difference, multiply x power minus alpha j alpha of x. This becomes x power alpha. In this case, what happens? X power minus alpha, and you have a minus here, j alpha plus 1 of x. We will first see these two properties, and then you expand this side, left hand side, and if you add and subtract, it will give you two more properties. So, these are important. First, we will prove these properties. Simply multiply the first one. To get the first one, you consider this. So, we will prove the first one. So, proof of the first one is, you consider this x power alpha j alpha of x. What happens? This will be equal to m is from 0 to infinity minus 1 power m x by 2 power 2m plus 2 alpha divided by m factorial gamma of m plus alpha plus 1. So, if you differentiate this, so you have to differentiate this, this will become simply m is from 0 to infinity minus 1 power m 2m plus 2 alpha into x by 2 power 2m plus 2 alpha minus 1. Okay, what is the derivative? So, derivative is simply 1 by 2, derivative of x by 2. So, we have 1 by 2 divided by m factorial gamma m plus alpha plus 1. So, take this x power alpha out, x power alpha if I take it out. So, what you have is m is from 0 to infinity minus 1 power m plus alpha. So, what you have is this 2 goes here. So, you have m plus 1, this you can rewrite gamma m plus alpha plus 1, you can write as m plus alpha into gamma m plus alpha. So, this you can cancel. So, you have x power 2m plus alpha minus 1 divided by 2 power m factorial gamma m plus gamma m plus alpha minus 1 plus 1 I can write, and what is left is 2 power 2m plus 2 alpha. So, 2m plus 2 alpha minus 1. So, when I multiply x power alpha, so it's actually only here, not for the full. So, this is only x power this 2 power 2m plus alpha. So, only 2m plus alpha. Okay. So, you have only, this is only for x. So, you have only x 2 power 2m plus alpha. Okay. So, if you differentiate here, so 2m plus alpha, so minus 1. So, this is what you get, and you have 2 power 2m plus alpha. So, this is right. So, you take x power alpha out, you have this, and this you can write like this, you have 2m plus alpha. Okay. So, this is it. So, this is equal to x power alpha times, this is exactly equal to alpha is replaced with alpha minus 1. Wherever you have this you have alpha minus 1. So, this is nothing but j alpha minus 1 of x. So, what you have is this is not minus alpha, this should be alpha minus 1. Okay, so, there is your first property is done. Second property proof is also something similar. You multiply x power minus alpha to j alpha. So, if you do that and differentiation with x power minus alpha j alpha of x, what you get is d dx of simply m is from 0 to infinity. What you have is minus 1 power m x power 2 m plus alpha. When I multiply with x power minus alpha, this goes divided by 2 power 2 m plus alpha, okay, because that is in the j alpha, m factorial gamma of m plus alpha plus 1. Okay, so, this you have to differentiate. So, this will give me, if you differentiate, so m equal to 0, that is going, if you right. So, what you are left with is only m is from 1 to infinity minus 1 power m 2 m x power 2 m minus 1 divided by 2 power 2 m plus alpha m factorial gamma of m plus alpha plus 1. So, this is it. So, if you change the index, you are done. So, what you need from m is from m equal to 0, even if you are if you differentiate. So, you can see that x power m equal to 0, that is simply a constant. After differentiation it will go. So, x square. So, you only have m equal to 1. So, that is what you have. So, now you change the index and rewrite. So, if you write the index, where is that x power minus alpha gone, right. So, you have now you take what you want is, when you multiply and differentiate, you want x power minus alpha out. So, you take that x power minus alpha out, x power minus alpha, if you take it out, you have to add. So, I have to add 2 m x power 2 m plus alpha minus 1 and divide by 2 power 2 m plus alpha m factorial gamma of m plus alpha plus 1. So, now you change the index. So, if you change the index, what you get is m equal to, you replace m equal to m plus 1, then it will become m is from 0 to infinity minus 1 power m plus 1 2 into m plus 1, right. So, x power 2 m plus 2 plus alpha minus 1 divided by 2 power 2 m plus alpha plus 2, because 2 m plus m equal to m plus 1. So, you have m plus 2, 2 m plus 2 plus alpha m plus 1 factorial gamma of m plus 1 plus alpha plus 1. So, this is what you have. So, this is equal to minus 1 power m. So, in that you take it minus 1 minus out. So, what you have is m is from 0 to infinity minus 1 power m 2 1 goes here. So, it will be 1, okay, and this goes to m factorial. So, you have m factorial, okay, x power 2 m plus alpha plus 1, okay, divided by 2 power 2 m plus alpha plus 1 into gamma of m plus alpha plus 1 plus 1, okay. This is nothing but minus x power minus x alpha j alpha of plus 1 of x. This is what you have, you need, okay. So, this is your second property, okay. So, using this we will show, we need these properties to show that these functions, orthogonal property of these functions, just like you had legendary equations, Legendre functions you had Legendre polynomials, Legendre bounded solutions which are Legendre polynomials. J they are Pn of x, n is running from 0, 1, 2, 3 onwards. They are countable number of polynomials. They are orthogonal to each other with respect to -1 to 1, okay, the dot product. So -1 to 1 you have seen, right. So based on these properties we will prove this orthogonal relation which you have seen for Bessel, which you have seen for Legendre equation. So similar such thing we will do here. Before I do this, we will have Bessel equation. So Bessel equation is x y double dash plus x y dash plus x square minus alpha square into y equal to 0. So this is what is the Bessel equation. So right, so you have a Bessel equation like this. So you can modify this Bessel equation like this. So if you do it, so you have you can replace x by lambda t. If you do, let x by lambda t. If you do that, what happens? If you use that, x square is lambda square t square, dy by dx. dy by dx is equal to dy by d lambda t. So this is equal to dy by dt by 1 by lambda, right. So similarly, d square y by dx square is equal to 1 by lambda square d square y by dt square. So you will see that d square, this is you have 1 by lambda square d square y by dt square plus here also. So you have lambda x is replaced with lambda t, dy by dx will be 1 by lambda times dt, okay, if you use this one here, plus lambda square t square minus alpha square equal to into y equal to 0, okay. So y is a function of t now. So this goes, lambda goes. So what you end up is t square y double dash. Now the y double dash means d square y by dt square plus t y dash plus lambda square t square minus alpha square into y equal to 0. So this is why this is the called modified equation, modified Bessel equation. You can see that x is always positive, okay, and so here also if lambda is okay, if you can take it as positive, okay, lambda is positive and t is also positive. So if lambda is fixed, you fix this with this transformation. If x is the domain is x positive, so that makes it t is also positive. The domain is always, this is the domain for which you have so with this some lambda positive. If you choose, your domain is t positive. So this is the modified equation, okay. So once you have this, what are the solutions here? The solutions are, so you know that what are the solutions here. So these are j alpha of x are solutions, right. J alpha is a solution, right, is a solution for this equation. So then correspondingly I should get here j alpha of lambda t is a solution, okay. So here I fix now. So this is what I do. I fix my alpha here and I fix the domain. So then I have a domain t greater than t. I choose some L, okay. I fix some number L which is positive, okay. So in the domain I have t greater than equal to 0. This is a full real line. In that I fix this L, okay. So if I do that, so you have j. So now you look at this this x positive. So this has roots, okay. So this is corresponds to x positive, okay. This corresponds to x positive. You have the roots of this j alpha are x1, x2, x3 and so on. You call this, okay. Then what happens is that once I fix this number L, j alpha of some lambda I of L will be 0. What is lambda I L? Is actually equal to xi. So, xi I know that is the root, okay. So, that will make lambda I is xi by L for every I 1, 2, 3 onwards. So, if you know these roots of this j alpha of xi's are 0, then I can fix this L and make my lambda is like this. Then I have j alpha of lambda I L equal to 0 for every I 1, 2, 3 onwards, right. So, because lambda i's where lambda i's are xi by L, okay. So, lambda i's are this. So, you see that if I fix the domain L and if I fix my alpha, I have infinitely many functions, okay. So, what are those functions? J alpha of lambda I x, okay, j alpha of lambda I x for every I 1, 2, 3 onwards, okay. Where is this? These functions are defined, x belongs to 0 to L, okay. In fact 0 is also there. So, let us because as a function is also included, 0 is also included. These are the definitions. So, these are the functions, okay. These functions, these Bessel functions, when you fix alpha and in this domain these functions are orthogonal with respect to. So, orthogonal means, this means they are from, what is the domain? 0 to L. You take any, alpha is fixed, lambda I x, okay, alpha is fixed, lambda j of x. This dx with the weight function x, in this sense it is 0 for every I not equal to j. Whenever you choose this, lambda i's are different, okay. So, it is 0. If it is I equal to j, it is non-zero, okay. So, it is something else. What happens to that? So, 0 to L x j alpha of lambda i's of x square dx, you will have something, okay, something we will prove what it is, okay, something we will see, some constant, we will see what it is later. So, we will first prove the first part, that these functions. So, I write it as a result, the functions j alpha of lambda I x when x belongs to 0 to L, okay, are orthogonal, satisfy, or rather you say satisfy integral 0 to L x times j alpha of lambda I x, j alpha of lambda j of x dx equal to 0 for every I not equal to j, where alpha is fixed and L is fixed. So, if you fix your alpha and the domain some point L, you have orthogonal functions, okay. These Bessel functions are orthogonal in that domain. So, you can choose infinitely many such class of orthogonal functions, okay. Just by changing alpha and L, you can have infinitely many orthogonal functions, okay. So, for each alpha and L you can have, so you can have, because j alpha of x has infinitely many roots, for each root you have such a function. So, for each root xi there is a corresponding lambda I. So, for each lambda I you have j alpha of lambda x. So, for each root of the equation you have one function. So, that means for each fixed alpha and L you have infinitely many roots, that implies infinitely many functions and which are orthogonal, okay. So, every fixed alpha and L you have a class of functions, orthogonal functions. Similarly, so like that So, we will first see these functions, these orthogonal we will show that these are orthogonal. So, this is straightforward. So, what is j alpha of lambda I x? This satisfies this equation, right. So, this is the equation it satisfies. So, you take this one. So, how do we prove this is we simply show that j alpha of lambda I x satisfies x square. So, instead of t I have x, okay. So, it does not matter. So, x square j alpha double dash of lambda I x, okay. That is what you have, right. So, you see that j alpha of lambda t satisfies this equation, that is d square by dt square of j alpha of lambda t. So, I have x square here, just notation change, instead of x instead of t I am writing x square into j alpha double dash, that is d square by dx square of j alpha of lambda I of x plus x times j alpha dash of lambda I x plus x square minus here this corresponds to lambda I. So, this is lambda I square x square minus alpha square into j alpha of lambda I x equal to 0. So, if it satisfies the equation here, if it satisfies this equation, that is what you have to write here. So, that is what you have written. So, similarly j alpha of lambda j of x satisfies x square j alpha double dash of lambda j x plus x times j alpha dash of lambda j x plus lambda j square x square minus alpha square times j alpha of lambda j x equal to 0. What I do is I simply multiply j alpha lambda j here, okay. For this equation you multiply simply j both sides j alpha of lambda j x, and here you multiply j alpha of lambda I x, okay, equal to 0. So, both sides if you multiply there is no change, okay. This satisfies equation implies this, satisfies equation implies this. For this I multiply both if j alpha of lambda j of x satisfies this, that you multiply to that equation, and whatever is satisfied for this equation here, this equation j alpha of lambda I x, you multiply to this, and then you take the difference, okay. So, this is equation number 1 and 2. 1 minus 2 will give me, what happens 1 minus 2? So, simply x square j alpha double dash of lambda I x j alpha of lambda j x minus j alpha dash of lambda j x j alpha of lambda I x. This is what you get, plus x times again here. So, j alpha dash of lambda I x j alpha of lambda j x minus j alpha dash of lambda j x into j alpha dash of lambda I x. That is what is this difference, plus, so alpha square this will be 0 because of both are same. So, j alpha lambda j alpha lambda I, here also you have this same. So, we have lambda I square minus lambda j square, other thing is common, that is x square j alpha of lambda I x into j alpha of lambda j x equal to 0, okay. So, here you can cancel one x you cancel. So, that means, and you can see that x times, okay, x is what you have is, if you do that, x times j alpha dash of lambda I x j alpha of lambda j x minus j alpha dash of lambda jx into j alpha of lambda ix. You consider this function, you differentiate this with x. If you differentiate this function, this is a function of two functions, multiplication of two functions. If you differentiate, derivative of this is, if you differentiate, so first you differentiate x, that will be simply this part, that is, that you already have here. Okay. If you differentiate this one, what you get is this one. You can easily see that. Okay. So, if you differentiate this part, what you get is j alpha double dash of lambda ix, okay, into j alpha of lambda x minus this one. If you differentiate, this is what you will get. So, these two terms I can put it like this, plus lambda I square minus lambda j square into x into j alpha of lambda ix, j alpha of lambda jx equal to 0. You simply integrate both sides from 0 to L dx, integral 0 to L dx. Okay. And what happens? Because j alpha of lambda j L, these are the roots, right, lambda j L, that is how we have chosen your j alpha of lambda I L for every L. So, j lambda, when you put x equal to L, j alpha of lambda j or j alpha of lambda I L will be 0. Okay. So, at L this part will be 0. When you put x equal to 0, x into whatever may be the quantity, its derivatives at 0, it may be 0. Okay. So, overall this quantity will be 0. What is left is the other part, that is lambda I minus lambda j whole square, lambda I square minus lambda j square into this integral. There is a constant, I take it out, x times j alpha of lambda ix, j alpha of lambda jx dx equal to 0. Because I is not equal to j, this cannot be 0. Okay. If I is not equal to j, lambda is certainly not equal to lambda j, because lambda is nothing but xi by L, right. So, what is your lambda I? Xi by L. So, xi by L is not, cannot be same as xj by L, because these are distinct roots, that is how you have chosen. For x1, x2, x3, these are all distinct roots of j alpha of x. Okay. So, because they are distinct, xi's are distinct, lambda's are distinct, that is, so if lambda is I is not equal to j, this is because of this cannot be 0. So, this whole thing is 0. So, this implies this integral has to be 0. That means these functions, when I is not equal to j, they have to be orthogonal. J alpha of lambda jx dx equal to 0 if I is not equal to j. This is called orthogonal relation. Okay. So, what happens if I equal to j, we can show that integral value will be some constant that you can find out. So, that I will do in the next video.